Hi guys, today we're going to talk about solving linear inequalities and combined linear inequalities, kind of a two-part thing a little bit, just to refresh your memory. So remember that solving inequalities is similar to solving equations. The goal is still to isolate the variable, whichever variable that may be, on one side of the instead of equation. Now we're going to call it an inequality. Just imagine that your less than or greater than symbol is replacing the equal sign. So if you say x is less than 3 in symbols, that looks like x is less than, always points to the smaller one, less than 3. And remember that you read from left to right. So if your variable ends up on the right side, then you may want to just kind of reverse the order. And if we look at that on a number line, if this is 0 and here's 3, we would put an open circle at 3. And we would shade everything on the number line to the left of 3 because that represents all the values that are less than 3 and not including 3, which is why we have an open circle at 3. If we say x is less than or equal to 3, that means that it could be 3 or it might be any value that's less than 3. So we would actually have a closed circle on 3, and we would shade, again, everything to the left of that, which represents all the numbers that are less, right? If we'd want to talk about x is greater than 3, then on the number line, again, we would have an open circle at 3, but the values that are greater than 3 is everything 4, 5, 6, 3.5, 3.01, all of those to the right of 3. And if we want to say that x is greater than or equal to 3, it means it can be at least 3 and anything bigger than 3. So we would have a closed circle when we graph it on a number line and shade everything to the right of 3. Got it? It's a good idea to put your variables on the left side just so that you can interpret the symbols a little bit easier. If you choose not to do that, you just may run into some difficulties when you graph. The reason why having the variable on the left for inequalities in particular, not necessarily equations, but particularly for inequalities, is because the direction of the inequality kind of points in the direction that you have to shade your number line in, right? So if it says less than, you're shading to the left, and if it says greater than, you're shading to the right, and it kind of points and helps guide your direction when you're graphing on the number line. It's not necessarily a requirement, but it is really useful, and you should in general, solve your inequalities by putting the variable on the left. So the one way in which solving inequalities differs from solving equations is when you have to divide or multiply by a negative number, right? So negative means we're kind of doing the opposite. And in this situation, we're going to change the direction of the inequality symbol. So if it's a less than and you have to multiply or divide by a negative number, then you're going to change it to a greater than, et cetera, et cetera. So we're going to practice a couple of these and just see how they play out, see if we can experience a little bit of each of those things. So we're going to solve it in the usual fashion. So we're going to solve 3x minus 5 is greater than 15. We're going to start by adding 5, and we get 3x is greater than 20. And then, of course, we're going to divide everything by 3, and we get x is greater than 20 over 3. So that's just your basic inequality solution. If you have to write it in set builder notation, it looks like this. We say the set of all x such that, so you might see it as 2 dots, you might see it as a long single vertical bar such that x is greater than 20 over 3. And that's what it would look like in set builder notation. I do think that in the program in which you're working frequently, you're going to have to just fill in the inequality part. So you're going to focus this, and then they're already going to have it set up as set builder. So you want to graph that on the number line. We need to think about where 20 over 3 would be. So if you want to convert that a little bit to a mixed number, 3 goes into 26 times, and you have a remainder of 2, so 6 2/3, right? So I'm going to put 0 here, and 3, 6. 6 2/3 is going to be slightly bigger than 6. So I'm just going to put an open circle here, and we want to shade everything to the right because we want all values that are greater than 6 2/3. So this would be 20 over 3. I'll just mark that on the number line like so. All right, moving on to the next one. Let's talk about solving b. 2 times the quantity 5 minus 3x is greater than 34. Start by distributing the 2. 10 minus 6x is greater than 34. Subtract your 10 from each side. negative 6x is greater than 24. Now we need to divide everything by negative 6. Watch out. Remember, this is the one that you're going to watch out for because you are now dividing by a negative number. So you have to change the direction of your inequality. X is less than negative 4. X is less than negative 4. That's the key thing that happened there, is that we divided by a negative 6, so we have to change the direction of the inequality. So here's 0, negative 2, negative 4, negative 6, less than negative 4. Negative 4 is not included in part of the solution, so I'm going to put an open circle on negative 4 and shade everything to the left, which represents all the values that are less than negative 4. Okay? Last one on linear inequalities before we start talking about combined inequalities. The last one we'll do is 4x minus 12 is less than or equal to negative 6x minus 3. So I'm just going to work this right side first and distribute the negative 6, negative 6x plus 18. Then I'm going to combine terms on the same side. So I'm going to add the 6x to each side so that it will cancel on the right. And I'll get 10x minus 12 is less than or equal to 18. If you want to go ahead and add the 12 at the same time, it's fine. Or you can do it step by step. So you get 10x is less than or equal to 30. Divide everything by 10, obviously, and then x is less than or equal to 3. So in set builder notation, it would look like the set of all x such that x is less than or equal to 3. If you're working the program, in general, all you might have to fill in is this inequality in the box. It may already be set up in the program for you to type in x is less than or equal to 3. So here's 0, 3. Since it's or equal to, it can be 3, which means 3 is included in the solution. And everything then also less than 3 is to the left of 3. Got it? All right, next thing we're going to talk about is solving combined inequalities, conjunctions and disjunctions. A conjunction is an and statement. This is the and statement. And a disjunction is an or statement in mathematically. So to solve a conjunction with two open sentences, you have to find the values of the variable for which both statements are true. So mathematically, when we talk about and, every part of it has to be true in order for it to be true at all. When we talk about or, only one little piece of it. You can't think about the disjunction mathematically in terms of situations where somebody is giving you a choice between two things and you can't have both. Mathematically, that's not necessarily the case. Mathematically, it's just at least one has to be true for a disjunction. So let's talk about a conjunction first. We're going to solve the conjunction negative. Well, this is already solved, but we want to talk about what it looks like on a number line. And then I'll see if I can make up another one just for you to see what it looks like. So negative 2 is less than x, and x is less than 3, right? So we want values that are such that they satisfy being x being greater than negative 2 and x being less than 3. X is greater than negative 2 and x is less than 3. So another way that you're frequently going to see things written like this is in a three-part inequality with less than symbols on each side of a variable in the middle between some expressions. And we'll come up, I'll see if we can come up with one in just a minute just to work with it a little bit. And I'll go ahead and graph this one. This looks like negative 2, 0, 3. Remember that negative 2 and 3 are not included in the solution. So we're talking about values that are greater than negative 2 and at the same time less than 3. So values that are greater than negative 2 and at the same time less than 3 are the values between negative 2 and 3, which is why I really like this form, this combination where the variable looks like it's between the two values. So let's see if we can make up another one. Let's say that we have 5 is less than 2x plus 3, which is less than 7. Okay, and we want to solve this combined inequality. You can work it just like this. You don't need to pull it apart. Just be careful. You're trying to get x in here by itself. So I'm going to subtract 3, and whatever I do, I need to do that in all parts. Okay, so then I get 2 is less than 2x, which is less than 4. And then I'm going to divide every term by 2. And then I end up with 1 is less than x, which is less than 2. On a number line, of course, that would just look like you'd have value at 1 and at 2, open circles, and shade everything in between. And if you had or equal to bars underneath your inequality, then you would have closed circles, and that's all that that would mean. So I really like to solve it with the variable in between the values, but it's up to you. You can separate it if you prefer. Notice that when you have an and statement, both parts have to be true. For a disjunction, you want to find the values of the variable for at least one of the statements to be true. So in this case, we're talking about x is less than -2 or x is 3, which means we could have solutions that are to the left of -2 or solutions that are to the right of 3, solutions that are greater than 3. Your disjunction cannot be written as a combined inequality without the word or. You're always going to see that word or there, okay? So you might have, let's say you have 3x minus 7 is greater than 5, or 2x plus 1 is less than -7. So in this case, if we solve this disjunction, for example, we're going to have to solve each one separately. So I would add 7 here, and I'd get 3x is greater than 12, divide by 3, and x is greater than 4. And then I have to solve the other disjunction, the other inequality that's part of the disjunction. Subtract 1 and get 2x is less than -8 and x is less than -4. So in this case, I'd have an open circle at -4 and an open circle at 4, and I would shade to the left of -4 and to the right of 4. There are a couple of crazy kind of scenarios, a little bit, where you have some unique situations where there's no solution or all real numbers. Make sure that you satisfy the equations of the conditions of the inequality. So if we have x is less than 2 and x is greater than 5, can you think of a number? What number is less, smaller than, and at the same time greater than 5? So at the same time, more than 5, right? 6 is more than 5, but it's not less than 2 at the same time, right? So in this situation, there is no solution. No solution. There is no number that's less than 2 and at the same time greater than 5. And then in that case, there would be no shading on the number line. If you have a number line, there would be no shading on the number line, okay? All right, so let's talk about this particular disjunction. X is greater than 3 or x is less than or equal to 6. So if you look at those kind of independently, x is greater than 3. Let's look at x is greater than 3 separate from x is less than 6. So if we look at x is greater than 3, here's 0, here's 3, here's 3. Everything to the right of 3. Now let's take a look at what would happen if we're looking at the 6. And we have 0, here's 3, here's 6, less than or equal to 6, right? So if I try to combine these a little bit on the same number line, what ends up happening, I'll put 0 here, 3 here, and 6 here. What ends up happening is that I have this open circle at 3, and I would shade everything to the right. That's everything that's greater than 3. Or everything that's less than or equal to 6, I'd put a closed circle on 6, and then I'd shade everything to the left of 6, everything that's less. And what ends up getting shaded on the number line? Everything. Everything ends up getting shaded. So the solution is all real numbers. You're going to learn in Algebra 2 how to talk about interval notation, and that would be more appropriate in this situation. The solution is all real numbers. You can find a number that will satisfy either being greater than 3 or being less than or equal to 6 every single time. Okay? And let's just try a few more We're going to solve and graph and express the solution in set builder notation. So notice that this is a conjunction because I have two less than symbols, and it says -5 is less than or equal to 3x plus 1, and 3x plus 1 is less than 4. If you want to separate it, you may. I like to really work it just like this. I'm going to subtract 1. And whatever I do, I need to do that everywhere. So I get -6 is less than or equal to 3x, which is less than 3. And then we divide everything by 3. And whatever we do, we make sure we do it everywhere. And we get -2 is less than or equal to x, which is less than 1. And on the number line, we've got -2, 0, 1. We should have a closed circle at -2 because it's included in the solution with the bar underneath that inequality symbol. We should have an open circle at 1 because it's not included. And then we're going to shade everything in between. These are all the values that are between -2 and 1, all the values that are greater than -2 and at the same time less than 1. And that's really what this means when you're trying to interpret this in trying to understand kind of what that means. In set builder notation, it's going to look like the set of all x such that, and you would just write this, type that in your box, that inequality right there. That's probably all you're going to have to do. But it does mean all numbers that are greater than -2 and at the same time less than 1. Greater than, I should have said greater than or equal to -2, right? Or less than 1. Okay? Let's try another one. We're going to solve, graph, and express in set builder notation. Notice that this is a disjunction because we have the word or right there. So we're going to distribute 2 minus 2y is greater than or equal to 6. I'm going to go ahead and solve this all the way out. I'm going to subtract 2 and get -2y is greater than or equal to 4. Then divide by -2 and get y. Okay, notice here's what I'm going to do. I'm dividing by a -2. And if I'm dividing by a negative number, that means I've got to change the direction of my inequality symbol. So y is less than or equal to -2. There we go. Now let's try the next piece. We're going to subtract 3y. Subtract 3y. And then we're also at the same time going to go ahead and add the 5 so that we can just simplify our lives a little bit. So we get y is less than or equal to 4. And then we're done. So I'm just going to bring that down here. Y is less than or equal to 4. So we've got y is less than or equal to -2, or y is less than or equal to 4. This one's a little bit quirky because we have a less than in one piece and also in the other. So remember that you just need to satisfy one of these if we have a disjunction. This one's a little bit crazy. So if we talk about numbers that are less than or equal to -2 or less than or equal to 4, we want the solution that's going to be the most inclusive. And the most inclusive solution is going to be the one that includes 4 and everything less than that, because we could, if we're picking a number and we want to pick a number that's less than or equal to -2 or less than or equal to 4, we could pick -5, we could pick -4, we could pick -17, of course. But we could also pick 0. 0 is less than 4, even if it's not less than or equal to -2. And 3 is less than 4, and 2 is less than 4. All of those. So if we want to express this in set builder notation, this would look like the set of all x such that, excuse me, I should have said the set of all y. Here's the proper variable. Set of all y such that y is less than or equal to 4. And I would have just written both of them if it were a disjunction in the true sense of the word, where you were shading different parts of the number line. That's it. And that's all we got for today on solving linear inequalities.